All right, so today we're going to look at one of the major applications of exponential functions, exponential growth functions, particularly with word problems, because this is a very real life applicable sort of thing. Okay, so exponential growth function. So this is a basic function. You're going to notice a little farther down the page that there is one for compound interest. We'll get to that in a minute. Okay, but these are actually very, very similar functions. Okay, so when you're going to look at these, personally, I just sort of remember this one and then apply it with this guy. And we'll talk about a little bit more what that is in just a minute. But just be aware that there are different functions, and you do need to be able to use both of them and know when you need to use which one. Okay. All right, so let's take a look at this. So we got this function, and exponential growth is when you're starting with some amount and then it's growing by some percentage. Okay. So y is going to be the final amount. A is your starting amount of whatever it is. R is your rate of increase in decimal form. So like if it's 25%, 0.25. Okay. 1 plus R, this stuff in parentheses, that is called the growth factor. And then T is your time. Okay. And by default, time is set in years. Okay. So T is your time, and by default, it's set to years. Okay. All right, so let's take a look at this guy. So in 2005, we got the tuition at a school was this much. In the years that followed, it rose by 3% each year, okay? And we're going to write a model for this situation. So first off, we need to make sure that we are using 0.03 instead of 0.3 or whole number 3, okay? Then my model for the situation is we want to find the final amount, right? My starting amount was 8,500, so y equals your starting amount, and then parentheses 1 plus your rate of growth, which is 0.03, and then raised to t, the time. We don't know a particular time here, so that's going to be our other variable. So our two variables here, instead of y and x, it's y and t. Okay, and then we're just going to clean that up a little bit. So we're going to make it 8,500 times 1.03 raised to the t power. There's our model. Yes, make sure that you combine those two things together. All right, now we are going to graph this on our calculators. So grab your calculator. Let's talk about how you're going to push these buttons. So going into y equals, all right, I'm going to type in 8,500 and then times 1.03. Use your exponent button here, raised to the x. Even though we use t, you always have to use the same button for a variable on your calculator. All right, and then before I graph this, I want to think about what my window is going to have to be, right? We're starting at 8,500 and then growing, right? And we're looking at time for our x values. So for my x values, I'm going to start at -2 just so I can see where the x-axis is. But like, we're talking about time. We're not going to go back in time, right? We're going forward in time. So I'll stick with, I don't know, 10 for now. We'll see. My y minimum, the smallest amount it's going to be at is 8,500, right? So I think I'm going to go with like 8,400 just so, again, I can see where that starting point is. And then go up to, I don't know, 10,000 and graph it from there. And we'll see where we end up. Okay, here's our function. You can kind of see, right? Think about what we graphed before, right? My asymptote would come up this way, and then it's darting up over here, right? So it looks like I just actually need to go higher, right? If I want to cut out some of this dead space, I'm actually going to make this go a little bit higher. Like, I don't know, 15,000. See if that fits this window a little bit better. That was too much, right? Now I've got dead space up here. All right, so let's try, I don't know, 12,000. See if that's better. 10 was too small, 15 was too big. I feel like I'm in a retelling of Goldilocks and the Three Bears. The third one was just right. Okay, so here's my graph, right? So I went from like -2 over here to 10, and we started at 8,400, I believe, and our end game was 12,000. And our graph looks something like this. Lovely. All right, to the nearest dollar, what will the predicted tuition be in 2012? Well, we started in 2005, So 2012, that would be a time of 7. So we're just going to plug in 7 into this equation. So I'm going to do 8,500 times 1.03 to the 7th power. All right, and then our next question is, in what year will the predicted tuition be $15,000? Okay, and at the moment you have to be able to do this on your calculator. So what I'm going to do is I'm going to go to my calculator. I'm going to make a second line at 15,000. And then I know I'm going to have to adjust my window, right? Because we dropped past 15,000. So I'm going to bring this up to say 20,000 just so I can see. And I'm going to increase my X values so that hopefully I can see it there too. And we'll graph that. So here's my exponential decay function. There's my 15. Oh, and I can just see the intersection point, right? So I'm going to calculate option 5, intersection. First curve, second curve, yes. That intersects at about 19.2. Okay, so this gave me an X value. Would be the answer to that problem. Okay, make sure you answer the question they ask. Okay, so that's exponential growth, no big deal. Lots of things grow exponentially. So you're going to see lots and lots of examples, lots of money grows exponentially. Okay, so what we're going to look at next is something called compound interest. So let's go on a brief little tangent where we're going to talk about how interest works. Okay, so there are different types of interest that you can have to deal with sometimes. Okay, so first of all, you've got simple interest. Okay, so simple interest is basically the idea if we start with, say, $100, right? So all of these examples, we'll start with $100. And to make our lives easier, let's just say we're going to do, I don't know, let's go with a 50% interest rate. That's astronomical. It's amazing. I would love to have a 50% interest rate, right? Just to make our lives easy, we're going to start with that. And actually, let's go with $1,000. No, let's stick with 100. I'm indecisive this morning. What can I say? Okay, so simple interest says that after 1 year, so I'm going to make like a little table comparing years and money. Okay, so with simple interest, what happens is after 1 year, you start as well, you gave us $100 and we're going to give you 50% interest. And 50% of $100 is $50, right? So the next year, you're going to have $200. And the next year, you'll have 250. And the next year, you'll have 300. Okay? So simple interest, you take the interest off of how much money you deposit, and you just get that same amount every year. Okay? Now, the clever person, though, looks at this and says, well, wait a minute, right? Because say after, 2 years, right? 2 years, I've got $200. If I were to say withdraw that money from this account and then put it right back in, well, 50% of 200 would be $100. Then I'd be making $100 every month, right? And that's a lot more money. So I would rather withdraw my money and then put it back in so that I get a new interest rate to start with, right? So that's kind of the flaw with simple interest, is that it makes it so that you're like, okay, well, I want to keep like constantly taking my money out. Like every year I want to take my money out, put it right back in, just so that I'm going to get a higher amount of interest. Okay, so simple interest, the interest is based strictly off of the principal, which is the fancy name for your initial amount. Okay, it doesn't take into consideration any interest you've earned. So even though you've got $300 now, they look at it and say, well, you only put in $100, so you're only getting 50% of $100 in interest. That extra 200 bucks we gave you, that was interest we gave you, and you're not going to make money off of the interest we gave you. Okay? So that's what simple is. So then we've got something called compound interest. Okay, and the idea of compound interest is that, yeah, you could keep pulling your money out and then redoing your interest rate from there. So compound interest, same deal, easy numbers, 50% interest, $100, right? With compound interest, you start with 100 bucks. After the first year, you get 50%, so you're still at 150. Okay? But then the next year, instead of giving you 50% of how much you started with, they give you 50% of this number, which is 75 bucks. So instead of getting $50, you get 75. So now, instead of being at $200, now I have $225. Okay, and then the next year, same deal. Instead of giving you that 50 bucks, they're going to give you half of this. So half of this number would be about 112. So we'd be up to about $337, right? And then the next year, they're going to give you half of this again. So half of that's like, I don't know, 160-ish, just making easy numbers. So about 160-ish, right? That's going to put you at about 197-ish, a little bit more than that. Oops, 497, okay? So when you compare, like, that's a big difference. There's a huge difference between simple interest and compound interest, okay? So that's what the difference is between these. So when you look at interest rates, to find simple interest, it's really easy. You figure out what 50% is, and then you add that a whole bunch of times, right? Compound interest, though, to calculate is a little bit more complicated, okay? And that's where this lovely formula comes into play, right? So in this formula, A is your final amount of money. So A is the amount of money left. P is principal, okay? And principal is the fancy bank word for your starting amount of money, okay? R is your rate of interest. N is the number of times your interest is compounded per year. We'll come back to that in just a second. And then T is the number of years. Okay, so N is the number of times compounded per year. Well, what does that mean? Okay, well, in this situation, we compounded our interest once every year, right? Every year, we reevaluated how much more money should you have, okay? What happens with compounding interest, though, is you could say, well, on the same logic we did before, right? We said if we kept re-pulling this money out and redepositing it, we get more interest, right? Well, couldn't I, in this situation, halfway through the year, pull my money out? Right? Because then I would have earned a little bit of interest. And then when I go to recalculate the new interest, I'm still going to get more money. Okay? So compounding interest, it matters how many times you're compounding. Compounding is just a fancy word for like recalculating how much money you've earned. Okay, so recalculating your interest. So when you compound, this is compounding once a year because every year we looked at it and said, okay, well, what's 50% of that number? Okay, but we could have done it instead. We could have said, well, let's take a look at it after half a year, and then after 1 year, and then after 1.5 years, and after 2 years, right? That would be compounded. This is compounded annually. Okay, this would be compounded biannually. Ooh, no, I'm sorry, semi-annually, twice a year. Okay, so that's what the difference is. If we said instead of going every half year, if we did every quarter year, that's compounded quarterly. Okay, so that's what we're talking about when we look at these different compounding rates. So that's what number of times compounded per year is. How many times are you reevaluating your interest? So let's take a look here. So this first example, $200 is deposited in an account that pays 3% APR. That's your annual percentage rate. Okay, so to the nearest dollar, how much will be in the account after 2 years if the account is compounded quarterly? Quarterly, 4 times a year. Okay, so that is telling us that N is 4. All right, now, what's this APR nonsense? Okay, well, APR nonsense is the bank looking at you and saying, okay, wait a minute, right? If you're putting this money in here and you're pulling it out halfway through, I'm not giving you 50% interest, right? You haven't had it in there for a whole year. If I'm giving you 50% interest for a year and you pull it out halfway through, I'm not giving you 50% interest. I'm breaking that interest up and I'm only going to give you part of it, right? So I'll give you 25% interest because you only had it in there for half a year, okay? So what's happening in our formula is we're saying, okay, take this annual rate and divide it by how many times you're reevaluating your interest. How many times are you compounding? So my equation is going to be, to find this final amount, I started with $2,000, right? I'm multiplying that by 1. The 1's for like 100% because you keep all the money you have. Plus 3% as a decimal is 0.03. So 0.03 divided by 4, because you're not going to get 3% every time, every quarter of the year. They're not going to do that for you. They're going to give you a quarter of 3% 4 times a year. Okay, and then we're going to raise that to the n times t. So this 4 shows up again times the amount of years, so 2 years. Okay, so why does that happen? Well, because when we're calculating our interest rate, if I'm going to say, give me my interest 4 times a year, then we shouldn't just be multiplying by 2, we should multiply by 8, because you're going to get interest 8 times over 2 years. Okay, lovely. So that's our setup. So now I'm going to pop all of this nonsense in my calculator and see what we get. So 2,000, parentheses, 1 plus 0.03 divided by 4, parentheses. And the only thing you got to watch out for here, all of this stuff, order of operations you're good with, right? You're multiplying in your exponent. Sometimes it will be easier to do that than to just do the math in your head. Okay, that will give you the same answer. If you type it in, right, and at the end you just put in 2 times 4, now order of operations isn't on your side anymore. Because remember, you do parentheses, then exponents, then multiplying. So you're going to get the wrong answer if you do it that way. Okay, so really important, either multiply this exponent in your head when you put it in your calculator, or put parentheses around it. Okay, so that works out to $2,123, and to the nearest dollar, that would be it. How much money there is. All right, uno mas. This one, how much should be put into an account? So how much should be deposited, right? That is what my principal is. That's my initial amount of money. So now I'm looking for what's my principal, 4% APR, so 0.04, compounded here, and then raised to the 12 times 3. Okay, so now we're going to do this calculating out, right? So first thing I'm going to do is put all this nonsense in my calculator. Okay, so I'm going to have 5,000 equals P, and then I'm going to calculate what is that. So 1 plus parentheses, 1 plus 0.04 divided by 12, and then raise that again. Either type in 36 or put parentheses around your 3 times 12. Okay, and that works out to about 1.127. Great. And now to get P by itself, this is P times that. So I need to divide both sides by that number, right? So I'm going to do 5,000. And I don't want to type, like, I don't want to do divided by 1.127, right? Because that's a rounded number. So what I want to do instead is use my previous answer. So I'm going to do second, and then the negative button to give me my previous answer. Okay, so to the nearest dollar, that would be $4,435. And there we go. All right, so that is a general idea of how compounding interest works. Okay, compound interest is awesome. Okay, you get a lot more money with compound interest than you do without compound interest. So it's definitely a good thing. All right, one more quick note. I said at the beginning, right, you've got these 2 different formulas. Okay, well, the easiest way that I think to do it is I just go off of this formula, Because what's happening here is it's just that your interest isn't compounding, right? So you're only getting that interest, this 3%, that's once a year. So I just think about it like I was putting it in here, where n is 1 for both of those, right? If n is 1, then it's just going to stay r, right? And if n is 1, it's just going to stay t. So it's the same thing. Sorry, you can't see that, right? Same formula if you consider that these problems are when you're compounding just once a year. Okay, so I just remember this one formula and use that